Always nice. Oh, okay. Sure. Even okay. Yeah.
Yeah, you want to have a shot?
Oh, yeah. Budget. Right now it's not minus. Oh, actually, that's a very much. Okay.
Recording in progress.
Do you have an HDMI cable? You can even reach out. Okay.
Hello, everyone. Welcome to the ML Systems and Optimization session. In this session, we have 5 interesting talks lined up. And with that, let me invite our first speaker, Wei New, and he's going to talk about some smart memory optimization techniques. So Wei New, take it away.
Okay, yeah, thank you. So, hello everyone. Today I'm going to present our paper, Smart Memory Layout Transformation, Elimination, and Adaptation for Efficient Data Execution on Mobile Devices. And this work is a joint work among 4 universities. I'm from University of Georgia and also your NC State University and the University of Texas Arlington and William Mary. We work together for this project. And we have been seeing the machine learning or artificial intelligence in our daily life. For example, for vision task or NLP task like text recognition, image labeling, and language identification, and smart reply. Among this application, the deep neural network is a key enabler for most of the scenarios. And for this kind of application, the performance is actually a critical factor to impact the user experience, especially for mobile devices, because the real-time execution is the most important criteria. And actually, back to 1960s, we have been seeing simple feed-forward network, and more recently, we have been seeing a lot of different convolutional neural network with come up with different capability to process different input. For example, the object detection and image classification. And more recently, one of paper attention is all you need, which I think most of people may heard about this paper. And they introduced a transformer, and it can be used in different domains like natural language processing and even the vision task. And more recently, there are a lot of different transformer variants. For example, transformer with global attention, with local attention, with even local attention, global attention, and cross attention, and different mechanism to process different tasks. because they have different capabilities with different attention mechanism. And among all of these, actually 4 different categories of different neural network, we have been seeing a key observation. That is, there are a lot of different layout transformation within the deep neural network. And here is just an example for transformer or attention block. For example, we have seen QKV and some softmax and matrix multiplication and get the final output from this simple graph. And we have been seeing 2 different layout transformation. One is explicit data reorganization. As we showing here, when we get a when we get some high dimensional tensor, we need to transpose or reshape it to some sort of shape which the succeed operator can take control. For example, the convolution, they may they can process 4-dimensional data, and the matrix multiplication can take 2 or 3-dimensional data to process. And before we join this or connect these 2 operators, we need to have a explicit data reorganization, like reshape and transpose. So this is the first category. And the first one is actually what we call it, the implicit reorganization. The implicit reorganization is because different operators, they have different preferability. For example, take we still use the convolution as example. They may prefer the NCHW or NHWC. This is some typical data format existing frameworks used. And matrix multiplication, they may prefer like NCH4 or different layout. And in this example, we show here, because the softmax, they prefer NHWC. So the inference or execution framework, they need to implicitly transpose this input data before feeding to the softmax to a preferable data layout, which softmax can execute it faster. So this is what we call it, the implicit reorganization. And this is just an example for the transformer block. It is also been widely seen in the traditional convolutional neural network as well. So what this key observation brings us the motivation, like on the mobile device or on the general platform, we have been seeing the 1-dimensional memory or 1-dimensional tensor. They have the spatial locality in the contiguous data, like the data before and after you access it, they may prefetch or store in the cache. However, on the mobile device, we have a specialized or specific memory, that is the 2.5D memory. Except for the 1 dimension, we have the height dimension and also the depth dimension, which is a fixed number of 4. So that is why we call it 2.5D memory. And the benefits of 2.5D memory compared to the 1-dimensional memory is 2.5D memory brings or has much higher bandwidth, and also it's much faster. The access time is much faster compared to 1-dimensional memory, the mobile GPU. And this 2.5D memory actually has been used in NVIDIA or the desktop level GPU as well. But because the shared memory on the desktop level GPU is much faster than the 2.5D texture memory, so most of the time we still use the shared memory on the mobile on the desktop GPU. And this data layout transformation is very, very expensive on the 2.5D memory on the GPU compared to 1-dimensional memory. You can think about we have a soft rope. And if you want to cut it into multiple pieces, or if you want to reorganize the data, actually for one-dimensional rope, you don't have to do a lot of things. You just need to cut it. And you don't even need to really reorganize the data. But for 2.5D memory, you have to do a lot of things, which is kind of similar to if you have a paper. You want to reshape the A4 paper into some different shape, then you need to cut more pieces. And even you need to reorganize the data because they have the spatial locality or more dimensional spatial locality. And this is our motivation. And here is a evidence to show what is the real challenge and what is the real overhead when we run the deep neural network on the mobile GPU with frequent data reorganization. Here, this table in the first column, we show the different models. We show 5 models here: 2 convolutional model, ResNet 50, RegNet, and 3D transformer model with different attention mechanism like swim, C-swim, and stable diffusion U-net. And here we can see in the last 3 columns, we've seen the the latency breakdown. The first one is the implicit data transformation. Second one is explicit reorganization, and the last column is actually the computation overhead. And the conclusion here is, even though we already applied the operator fusion, and it can save some can lead to some less intermediate result, but we can still see a lot of latency are spending on the either implicit or explicit data reorganization. And the data transformation overhead even exceeds the computational cost. So this is what in this paper, we addressed to fully eliminate the layout transformation overhead. So here comes up with our contribution. We propose a high-level operator classification to unveil the relationship between the computation and data layout, and also design a mechanism to eliminate the layout transformation and implement this on the real smartphone devices and achieve a significant speed up. So let's first look at the high-level idea. So the key insight here is we have many operators in the DNN domain, like convolution, batch normalization, matrix amplification. And the different operator, they have different sensitivity for input layout and its computational pattern. So one is a data access pattern, another one is computational pattern. So we divided these operators into 4 different categories, along with 2 dimensions. One is the computation performance, whether it's sensitive to the computation performance is sensitive to input layout or not. Another dimension is whether its output data can be variable or fixed. So basically it means whether we can generate the output layout as what we desired with any with or without overhead. So this is our operator classification. And as you can see, the convolution is in the first category, and the gather slice or reshape transpose, they are more like with fixed output data layout. So it's more like it's less flexible compared to the convolution, because the reshape and transpose, they need to do more data reorganization. And after we have this table, what we can solve is we still have 2 questions. Even though we classify them into different category, another 2 questions is how to know if a layer should be eliminated or not, and whether it's profitable or not, and what layout should be used for certain layers. Like as we said earlier, whether the softmax need to use what kind of data layout, and for convolution, what layout can be benefits for the execution. And the previous table actually bring us some motivation or build up the foundation for the following decision for the previous 2 questions. And here, these new 2 table shows what if a 2 operator with different categories, when they connect together, what is the action and what is the output layout? Because we need to recursively utilize this table and to apply to a whole computational graph. And here, the first table shows whether we need to eliminate the operator. And the second one is what output layout we should be used. And here is a simple example. For instance, if matrix multiplication followed by the reshape, and the action is we can eliminate the second reshape and transpose. And its output type is ILD variable. So we need to search the layout which will be used for the first matrix multiplication. And later we can apply these whole rules to the whole computational graph. Here is another optimization we proposed in this paper. So basically for the layout searching is an NP-hard problem. And the key insight here is we can force the producer to generate a layout based on the reduction dimension. The reduction dimension is how we access the data with by a contiguous way. So after our reduction dimension optimization, you can see the data access order, they are contiguous. So this is very friendly for the GPU and mapped to the 2.5D memory. We also defines the index dependence. We also have some index comprehension optimization, which is kind of similar to the strength reduction in the compiler, but we use the shape information and in the deep neural network domain to get the more aggressive optimization for the index. And finally, we compare the results. We evaluate 18 different models, including the generative model, generative AI models, compared to the MN, TVM, NCN, TF-Lite, and DN Fusion as well. So we actually performed 3 different tiers of mobile GPU because of the limited space, we're not able to report all of these results, and you can check our paper for the full result. And this one is a comparison with other frameworks and with the latency. So the unit of this one is the millisecond. As you can see, we can achieve up to 7.9 times speed up compared to other frameworks. And also for the transformer, the layout transformation elimination brings similar speed up compared to other layout selection. And for convolution, the layout selecting brings considerable speed up than the layout transformation elimination because the transformer has more reshape and transpose. So thank you for listening, and I'm happy to take any questions.
Any questions?
Hi, so great work. And so one question I had was, how do you classify operators into layout dependent or layout independent? Because, for example, softmax, my understanding is that it's basically a scaling operation. So how does it depend on the layout?
So this is a great question, and we had a formal definition about how to classify the operator into 4 categories. We have a formal definition for that in our full paper, and intuitively, different operator, they have different computation pattern, right? For example, you can use some tensor expression to express the operator for convolution for softmax, and there is the index relationship between the input and output tensor. So there is a clear relationship, and we actually summarize this. The intuitive idea is we summarize this relationship and provide the formal definition for that. Yeah, thank you.
All right, thanks.
All right, let's give another round of applause for our speaker. With that, let me invite our another speaker, Jiao, and he's going to talk about how he's fighting with silent data corruptions in deep learning networks.
Thank you. So today thank you. So today I'm going to present our work on Dr. DNA, trying to combat silent data corruptions in deep learning inference. So first question, what is silent data corruption? So a very simple example of silent data corruption, SDC, is that occasionally our computing system, being ASIC, CPU, or GPU, will compute a wrong result, right? A very simple example of 1 + 1 will give us a 3 instead of 2 because of a hardware bit flip, a hardware SDC, right? And the reason we are calling this error SDC is because this corruption or this error is very silent, right? It happens without any indications from the existing built-in error detection mechanisms from the existing data centers or existing server design. And this actually, hits and being reported by several industry hyperscalers, including Google, Meta, and Alibaba. And the root cause or the sources of SDC comes from a wide range, from And this could hit especially the industry hyperscalers, where each one of them have millions of servers running, especially nowadays, the large scale training jobs like Gen AI, right? And the potential outcomes of SDC is also become more and more severe. It can result into data loss, incorrect computations, wrong predictions if this is a machine learning, exam. The significant difference, in the output between the error-free one and the error-impacted one. And what's more important about SDC is suggested by its name is silent, is insidious, and is stealthy, right? So there are no existing error detection or reporting mechanisms existing in the servers or data centers that can detect or report this kind of SDC, right? So it's a direct quote from Meta, basically saying that this SDC requires usually, days, even to months to debug and to root cause or to trace this SDC. So in this paper, what we are actually trying to do is that instead of detecting this SDC from the hardware, we're trying to do this from a software perspective, right? And we are basically saying, if an SDC happening, and we focus on deep learning inference here, right? Well, our key hypothesis is, if there is an SDC happening during a deep learning inference, there is a certain unique signature, a DNA, right, of SDC that we can formulate, we can extract, and we can leverage, that we can use to detect SDC. And in this specific context, right, the DNA also happens to represent distribution of neuron activation, right, the DNA of SDC. So as you can see from the figure here, right, the DNA just represents the distribution. In this case, you can see the plot of the distribution of the neuron activations for each layer and cumulative for all the layers. There are two phases for Dr. DNA, right? The offline profiling phase is trying to run a bunch of input batches, a bunch of training data or whatever data that you have without any SDC, without any error, right? So we are trying to kind of establish a baseline, an error-free history of the DNA, right? Without any errors. And during the online phase, right, if there is an SDC occurs or happens, we basically say that the DNA will change, right? So then we do this like compare between error-free DNA and the DNA under the potentially error occurrence. And if there is an outlier or there is any abnormalities that we can detect, then we say, hey, maybe there is an SDC and we should alert and mitigate. So specifically, we formulate and develop the DNA by developing a metric that we refer to as abnormality score. And that's abnormality score is being computed per layer. And we also do a cumulative abnormality score for all the layers. Specifically, it breaks down into 3 different scores. And we'll go over them one by one. The first score that we are looking at is for each detection site. In this case, each detection site is a neuron that is being selected to focus in this case, right? So during the offline profiling phase, we are recording the historical distribution of the neuron activation for a given or for any detection site, right? The target neuron, and we plot, in this case, right, we plot the distribution of the neuron activation for that specific detection site. And then during the runtime, during the inference, we'll look at the same detection site and look at its activation again, and then we will see whether for this specific input or this specific inference, does the activation value falls into the a normal history that we did during offline profiling, or it falls out of the range of the historical profiling. So in this case, as you can see, we actually penalize, right, by putting a score, a positive score, to which we, in this case, right, to this detection site if the activation value is outside of the range of the historical distribution. And of course, right, in this case, we also use a 1 minus f, which is a frequency of that specific beam during the historical distribution. If that activation falls into one of the existing beams, but with a less frequency. So we say, hey, there is a high probability it still can be abnormal, even if it falls into an existing beam, but with a less frequency, right? So that is score 1. Score 2, instead of looking at individual neurons, we look at the combination of neurons per layer, right? So in this case, intuitively, what we are doing is just to simply compare the per layer DNA during offline profiling versus the per layer DNA during the inference time. So in this case, we're just doing an EMD, Earth mover distance, trying to calculate the distance or the similarity between the two DNAs. So in this, and this will be directly used as our abnormality score 2. And then the third score, in this case, we are looking at the extreme neurons, right? We define the extreme neurons as the neurons for each layer, as the neurons that have the max and minimal value for that layer. So during the offline profiling phase, for each layer, we find, hey, this index 10, index 20 are the extreme neurons. And during the inference, if this changes, if the extreme neurons are not 10 and 20 anymore, then maybe something happens, right? So we want them, if they are still if they are still being consistent, then we are saying, hey, the abnormality is less likely, right? So that is score number 3. And at the end, what we are doing is we take a weighted sum of all the 3 abnormality scores to formulate this, this total abnormality score, which is the DNA, okay, of the SDC. And then specifically, we are then using this DNA signature, right, to do SDC detection and mitigation. So what we do is that we are doing a cumulative, we're doing a cumulative sum, right, of the abnormality scores per layer, and compare this cumulative abnormality score with the accumulated abnormality score, between offline profiling and during the runtime. And if there is a certain margin, right, if there is a certain significant difference, then we say, hey, this is something worth to be noted, right? So we basically send an alert and say, hey, we should do some mitigation. Of course, right, there are a lot of existing works trying to do, especially in the fault-tolerant AI domain, they're trying to do error mitigations and error tolerance for AI. And, some of the most popular methods like activation filtering, basically setting a upper bound and lower bound for the activation using some fixed value. For example, like ReLU 6, right? And filtering any value outside of this, limit or this range. And there are, other traditional redundancy method like TMR or re-execution based method. So in this case, in our paper, we're actually trying to use DNA to automatically guide the existing method. For example, in the first method we're developing, which is called DAF, which is the distribution guided activation filtering. Instead of setting the fixed upper bound and lower bound, we're using DNA, the historical profiling to automatically, set and adjust the upper bound and lower bound for doing activation filtering. AR represents activation reassembling, which is when we detect SDC, we just randomly sample a value from the historical profiling of our DNA for the layer or for that neuron to replace the erroneous or the SDC value. So in terms of the experimental setup, we experiment with 10 different models across 3 different tasks, from vision to Gen AI, to segmentation. And we are experimenting with different fault models, from random bit flip, widely used, to random NaN, not a number, which happens, could happen to a floating point number. Random value and random value stealthy. So random value stealthy is even more, more harder to detect, because it's we limit the range of the fault. So the error, only has a very limited deviation from its original value. And you can see an example that if there's a random bit flip occurs, we can see the orange line and the blue line. There's a difference between 2 of them, right? So that's the margin. That's the margin that we can use and leverage to detect SDC. If the margin is large or significant enough, we say there is an SDC. And we also implement a 3 strikes and out rule, meaning if there are 3 layers in a row that exceeds the predetermined threshold, we say there is an SDC. And the performance, the Dr. DNA basically has a very high detection rate, greater than 90% for all of the cases, 100% for many of the cases. And we can also see the abnormalities score, T prime, with SDC is significantly higher than the error-free or SDC-free score, T. We also did, some ablation study looking at, for example, how many beans we should use for the for recording the history. So, we are experimenting a few different options, and it says that not, as usually we think as many as possible, but in this case, we have a sweet spot. Also, we do ablation study of number of detection sites we should use. So instead of using, many, or all the neurons per layer, we're only using a limited number that can yield a good enough results. And also we compare with the existing detection methods. We have a very good balance between detection rate as well as the overhead. One final example that we are showing is using DAF. We are able to recover a lot of erroneous cases in the Euro example. Final slides, right, showing the compare with the baselines. Dr. DNA achieves a very good balance between efficiency, detection rate. Because of the time limit, I won't go through the detail of the baselines, but feel free to look at the paper. TLDR of DNA, look at the silent data corruption using software and algorithm level signatures. And happy to take any questions, and feel free to catch me offline, and happy to take questions. Thank you.
So curious about 2 things. One is false positive. Second is that are you training when you are coming up with this signature or this DNA distribution, the one on which you are doing your detection, or?
Yeah, great question. So for the question number 1, false positive. And I think I mentioned that, so we actually, can see false positives, of course. So we're actually implementing, techniques like 3 strikes and out, this kind of techniques to reduce the false positive rate. And there are actually some hyperparameters, for example, the margin that we can use and set to, have a good balance. And actually, I think we use like 3% or something as the margin. So we have a very good balance. I think we limit the false positive rate to less than 3%, or 0.5% or something like that.
Right.
Question number 2.
Maybe we should take it offline.
Okay.
Oh, sure. Yeah.
Yeah.
Thank you.
All right. Let's thank our speaker once again.
Thank you.
With that, let me invite our 3rd speaker, Max Lam, and he's gonna talk about private information retrieval for on-device machine learning inference.
Sorry. Thank you. So trying to connect, but it's not doing so. I don't have, do you have it? Okay. Let's see. Sorry, that's reversed. Great. Hi, everyone. Thank you for attending my talk. Today, I'd like to talk about our paper, GPU-based private information retrieval for on-device machine learning inference. To introduce a broad context, on-device machine learning inference is a solution to privacy by keeping all of your data on-device and performing your neural network inference on-device. None of the user's data needs to be sent to a central server, which maintains privacy. Privacy might be motivated by certain regulations, laws, or policies that limit the amount of data that a central server can collect from a user's data device. For example, Apple's app tracking transparency feature ultimately limited the amount of data that meta servers could collect from users' devices, which ultimately severely impacted the way that Meta's recommendation models worked. And this can have a huge impact on a corporation's downstream revenue. For example, Apple's privacy push might have costed Meta at least $10 billion in revenue. And so on-device machine learning inference might be a potential solution for ensuring privacy in these scenarios and can potentially be a very effective way of managing these regulations or laws or policies. Unfortunately, the problem and challenge with on-device inference is that a lot of times the models might be too big to store on device. For example, your mobile device might only have around 512 megabytes allocated for each application. And so if your model is too big, on-device inference won't work. Particularly in the case of recommendation models, which are very crucial to companies like Meta or Google. Recommendation models require the use of very large embedding tables, which are used to map categorical features like user ID, product ID, or ad ID to numerical features, which are then used as inputs to the neural network for ad recommendation. Specifically, embedding tables across numerous different models, both public and private, may take up to gigabytes of data. For example, as you can see in the graph and the table and the numbers on the right, for a specific industrial grade recommendation model, this model takes up to like 5 gigabytes of storage and also uses multiple tables. And so because these tables are so large, it's impossible to really store them on a mobile device where you only probably have around 200 megabytes of data that are allowed per application. And so at the end of the day, you basically need to keep these embedding tables on the server. But this poses a challenge for privacy because now you need a way to really kind of look up these embedding entries in a private manner from these servers. Fortunately, this is kind of like a well-studied problem in cryptography called private information retrieval. And the idea is really for private information retrieval is that it allows private table lookups without the server really knowing what index the client requested. And in particular, in our paper, we focus on private information retrieval, or PIR, in a two-server private context. And in this context, we assume that there are two non-colluding servers holding a copy of the table. And what ultimately happens is this protocol, the client issues and uses a distributed point function and issues two keys which are sent to both servers. These keys are compact representations of the encrypted index into the table. And upon receiving these keys, the server evaluates these keys that expand out to secret shares of the one-hot indicator vector of the index that the user wants to access. And then the server does a complete dot product between the expansion of the keys against the entire table, and it returns the result to the user. The user sums together the result, and that gives them the final entry, the final true entry of the embedding that they wanted to access. And so a distributed point function, or a DPF, is extremely efficient in terms of communication. It requires only logarithmic communication in the size of the table. So if if the table size is like 1 million or 10 million, you probably need 20 times some constant factor of bytes to kind of transfer between the client and the servers. And typically, when evaluating a DPF, you're using a 128-bit computational security, which means you typically need, on average, 2 to the power of 128 guesses in order to crack the scheme. And so where this kind of all fits into on-device private machine learning inference is that whenever a client needs to access an embedding table entry, they would use a distributed point function or DPF to issue and look up a particular entry in the table that is stored on the server side. And then the servers return the result such that the client can access or reconstruct the embedding table entry, which are then fed into the on-device neural network, which are typically fully connected, so they're compact enough so that they can remain on the user's device. And so privacy is maintained in this scenario because private information retrieval is secure cryptographically. Unfortunately, DPFs or distributed point functions are extremely computationally expensive to evaluate on the servers. And this is because evaluating a DPF requires computing expensive cryptographic instructions, including pseudorandom functions like AES-128 or SHA-256. Diving into this a bit more deeper, evaluating a DPF requires evaluating all nodes of a binary tree where the number of nodes in this binary tree is equivalent to the number of entries in the table. And for every evaluation of a node, you basically need to perform a single AES-128 operation. And since you have potentially millions of entries, that means for a single table index lookup, in order to do a single private table lookup into this table, it requires evaluating millions of AES operations. And so if you have like millions of users, or if each user requires multiple accesses to the table, this is extremely computationally challenging. So our approach is to effectively leverage specialized hardware to accelerate DPF computation, particularly by using GPUs to really leverage and massively parallelize these operations. And in designing these GPU acceleration strategies, we leverage or exploit two sources of parallelism. The first source of parallelism is very straightforward, and it's batch parallelism, which is that you can evaluate multiple DPF keys in parallel. And this is a very standard technique in machine learning. And so this is kind of trivial to do. So we kind of assume that this is just done, and we won't expand on this further. A more interesting source of parallelism is parallelism within a single DPF expansion tree. And this is kind of an interesting problem and different from standard vector or matrix operations due to its non-uniform structure. Because as you can see, we're kind of trying to evaluate a tree in parallel. And there are different numbers of nodes across different layers of the tree, which means that there's a different number or amount of parallelism that can be exploited at different parts of the evaluation stages. And so what turns out to be the case is that parallelizing the DPF tree is kind of a non-trivial thing to do on a GPU. And to kind of give an example of this, I want to show two naive approaches that fail for interesting or surprising ways. Our first naive approach is to kind of evaluate each branch of the tree in parallel. And so the idea here is very simple, which is you have each thread of each core kind of be assigned to a different branch of the DPF evaluation tree, and all of them kind of just independently evaluate those branches simultaneously. And this approach is naive, and it doesn't work because two threads might evaluate the same interior node twice, which duplicates computation. It performs redundant work. And this approach is highly inefficient. So maybe to just have a sequential approach where you do or evaluate a tree at a level by level approach. And in this approach, you kind of just evaluate each layer of the tree in parallel and sequentially, where all the nodes of a particular level can be evaluated simultaneously in parallel. Unfortunately, this approach on the surface seems to be very, very good in terms of parallelism, especially when you reach the leaf nodes, where you have a lot of nodes that can be computed in parallel. But as you know, like if you recall, the number of entries in your table can be extremely large. And so when you reach closer to the leaf nodes, you have to keep all of the leaf nodes output in memory. And this is extremely expensive in terms of memory capacity, especially when you realize that you have to utilize, like you're also taking into account batch size. So not only do you have to materialize a lot of intermediate nodes outputs to memory, you have to keep a lot of those multiplied by the batch size that you're using. And what that ultimately leads to is a memory capacity. And when you reach a memory capacity issue, you ultimately have to reduce the batch size. And reducing the batch size reduces parallelism, and reducing parallelism reduces computational efficiency. And so our second naive strategy of performing a level-by-level approach doesn't really work very well because of memory capacity issues, which ultimately limits the batch size that you can use, limiting performance. Try to get around so that we can effectively use a large utilization. And so we came up with an approach called memory bounded tree traversal. You just do a depth first evaluation of the tree all the way, and the recall that the final operation that we want to do is we want to evaluate all of the leaf nodes and do a dot product between those leaf nodes and the big embedding matrix. And so what we could do here is basically what we're doing here is we're kind of evaluating in a depth first partial manner down to the leaf nodes of the tree, and then immediately fusing the DPF key evaluation with the final really maxing out parallelism by choosing K to be large enough to saturate utilization. And so results, we see that our approach is not only not computing redundant results, but also highly in terms of memory. And what this queries per second versus latency, we're getting very high GPU utilization by really maxing out batch size. And what that ultimately leads to is a 30x speed up over a 30. So in conclusion, on-device inference by itself is really not enough for privacy because the embedding of GPU acceleration. And our results show that by efficiently doing this operation, we're able to get an over 1 order of magnitude speed up over a multi-threaded CPU implementation. So the final takeaway is that in order to make these private inference systems